Oh, that's good.
But my income this year is going to be half of what it was last year. And last year was probably 60% of what it was the year before.
And are you working to make money or to keep active?
Both.
Both. Okay.
This is Dan. Can I ask you about those Apaches? Do you think it has anything to do with those bladder tanks?
No, they lost their infrared and they wrecked both of these.
Huh.
Oh, okay. You're an infrared guy. My brother has been used to fly Blackhawks, and something happened to the tanks and the drives, and there was something about a safety check, and he's been a big advocate for trying to improve the safety checks on these helicopters. And apparently there's a system where you can actually shut it out to do a safety test. And then if you don't turn it back on, you take off, you got no controls. And a helicopter went down near where he was working, and he got all hot and bothered about it. And they got mad at him for raising safety issues. So I'm just
these were training missions, one in California, one in Kentucky at Fort Campbell. And both of them were flying at night, and they were flying on infrared sensor I worked on before I went to FLIR, and it went belly up. And I'm thinking it lost power. I'm thinking, from what I've seen so far, Boeing is the culprit, not Lockheed Martin. But
wow. Okay. Those things are there's so many moving parts. It's probably amazing, but I'll let it go at that. Thanks.
What do we have here? I see Tim Wenzel and I see Vicky. And now the whole crowd is coming. Yeah. Is that you, Scott, taking charge?
Yeah,
there?
yeah. I figured I'd show your intro
Okay.
thing, if that's okay.
Yes.
So am I.
We could use more talks. After March 31st, we can use more talks. So if anybody would like to do a talk, take one that you already have done. You may think that it's boring or something, but I haven't seen anything that we've presented that didn't spark people's interest in some way. So,
And that's like the variety too, right?
Science is boring, Bruce. We've heard all the science there is. There may not be any more science. We're about done. Just
yeah.
mine.
Well,
Okay.
somebody told me he wanted to do a talk on the psychology of executive recruiting. This guy's an executive recruiter. I think it's Howard Edelman's brother, Paul. Apparently he has it figured out. Would think. So how many people do we have here? Let's see.
It's about time, Bruce.
22 it says here.
Okay, good. Well, welcome to Science for the Board tonight. I guess we have one more minute and then we'll get the introduction going.
So Bruce,
Yes, Judy.
I'm going to be giving a talk here where I live on microscopy and very, very small, beautiful objects kind of thing. I've given it before. I'm doing it, I think sometime in April. So if you think that, I mean, it's light, there are probably people here that know more than even I know about the super microscopes, but I have some good pictures and stuff. So if you're desperate, let me know.
Okay.
It's microscopy in the very, very small.
Well, any talks you do seem to be good, so I'd say.
Right. No, I'm just know that I'm talking to people, many of whom may know more than I do. But
That's
it's
okay.
still, I'm doing it here. I've done it before, so it's not a big deal for me.
Okay, great.
Keep in mind, let me know what your choice is, because it's just hard to be up this late. I've been
Yeah.
up since 5:30 this morning, Dave and I, so.
Oh, boy.
Yeah, that sounds like a fantastic talk, actually.
Okay, well, welcome to Science for the Board. This is going to be the second half of a talk by Scott Diamond, and we had to postpone it a few weeks ago, but John Miller is going to do the introduction. John?
Yes, thank you, Bruce. Well, I was to start off with to read his bio, which he just posted. Scott loves physics and math. He has been known to read technical journals for pleasure, as most of us. He has degrees in physics from UC Berkeley and a PhD from Stanford, but left the Bay Area in '89 for Oregon. When not exploring the outdoor activities, he works on special projects at FLIR, and he was in the past an engineering manager and a quality assurance manager. And he's one of the few of us that still hasn't been fired from FLIR.
I know, I was thinking about that.
I do take some umbrage with the renewable energy, because none of what he's going to talk about is actually renewable. When that photon hits the photovoltaics, it's gone. So anyway, turn it over to you, Scott.
All right, thank you. Actually, I'm going to mention that. All right, so thank you, everybody. The title of my talk is The Science, Economics, and Politics of Renewable Energy. So last fall, I thought, I like energy. I'll give one talk on energy. Well, energy is a massive subject. So that one talk turned into part one, which was conventional energy about 2 months ago. And then tonight, I'm going to talk about renewable energy. And then if you're not sick of me, I'd like to finish this up maybe in another couple of months and talk about energy storage. So renewable energy for tonight. This is the outline of my talk. The vast majority of the time, we'll talk about photovoltaic and wind. I'm going to have to talk pretty quickly. I'd really like to get through this talk in an hour. And so if you have questions, if you have something really quick, go ahead and interrupt. But last time we had a lengthy, really great conversation afterwards. So if you really want to debate a point, I'd say let's hold it, and afterwards we'll let those people that go, and the rest of us can continue to debate this topic. So kind of a little about myself. So this is a picture of me. The earliest picture I could find of me bicycling in 1964, and then a more recent one. And I think I'm pretty good at bicycles. But I'm certainly not an expert on energy by any means. So in this talk, I'm really going to provide kind of the basic background information. I wouldn't make any stock decisions based on what I'm going to share tonight. But I wanted to mention that we have a member of this group, Ripu Malhotra, who's with us tonight, who's joined us for the last couple of months, who is in fact an expert on energy. So let's see if I can get all this straight. Ripu has worked in this field for 35 years. He's a fellow at SRI. He's written this book that I read, which is excellent, A Cubic Mile of Oil. He was co-author on that. He has a blog and is an invited speaker. And I'm playing this up, Ripu, in hopes that you will offer to give us talk yourself in the future and kind of take this to the next stage. Okay, so this is something that came up at the end of the last talk, and every energy source has its drawbacks. And last time I showed this picture of protests at Diablo Canyon in the 1980s or 1990s. And after the talk, someone made the comment about fracking and how bad fracking was, and that you could cause earthquakes, and we shouldn't support that. And I think these are valid criticisms, but I'd also say the criticisms aren't just on conventional energy sources. All of these energy sources have their drawbacks. And so there are people that are actively protesting wind power, wind turbines, people that are protesting dams, people that are protesting solar. Nothing is perfect. They all have their drawbacks. And I think the point is for us to make informed decisions. And in this talk, I'll try and, as best I can, objectively give the pluses and minuses of the renewable energy sources. Okay, this is a chart that I showed last time, a range of power scales. And I'm not going to go through this in detail, but mostly what I wanted to highlight was the one point I have in red there, which is kind of, and I'll refer to this a number of times in the talk. If you think of a typical coal or nuclear plant, you're probably talking about 1 gigawatt of energy. All right, so this is to John's point. What is renewable energy? You know, sciences are pretty well defined. This is a term that's unfortunately not all that well defined. And as you know, John and I kind of got into this argument over email of whether this is the right word or not. And I see in Ripu's book he used different words as well. But I decided I'd look up a number of the definitions of renewable energy. And the one I like most is the one I've highlighted in red here, which I'll zoom up in the next page. Renewable energy is energy from sources that are naturally replenishing but flow limited. Renewable resources are virtually inexhaustible in duration, but limited in the amount of energy that is available per unit time. You know, I think that's a pretty reasonable definition that kind of captures what most people mean by renewable energy, and it excludes things like coal and things like that. So there are other definitions that are thrown around in this area, and unfortunately, they're often even more poorly defined. So renewable, we just talked about. The other word that people use quite a bit is clean energy, and generally by clean, they mean energy that doesn't pollute. And in pollution, I'm including greenhouse gases. And another term is green energy, which generally means energy from natural sources. Sometimes people mean it's the intersection of renewable energy that's clean. So I would say if someone uses one of these words, it's probably a good idea to ask them what they mean. But these are probably the most common definitions for these three terms. And since I'm a nerdy scientist, of course, I like to think in terms of Venn diagrams. So I have this Venn diagram. So this is showing all energy sources. And then renewable is, of course, a subset of all energy sources. And clean is a subset that's partially overlapping, but not fully. And then green is another subset, right? So looking at conventional sources, fossil fuels is something that's neither clean, green, nor renewable. Nuclear power is something that I'd argue is clean, but it's not green and renewable. Wind, I put squarely in the intersection of all three of those, at least for now. Ethanol, you know, that's green and renewable. I think there's a lot of pesticides and stuff that use in ethanol, so I put it as not clean. And hydro, I put on the border between clean and not clean. But I'd say, you know, as I said before, every energy source has its drawbacks, and so people have differing opinions. Those people that protest, you know, they would say wind energy is not clean, and ethanol, some people would say, well, I don't know, you know, you're growing crops is fairly clean. So again, there's a lot of debate as to whether things are clean or not. So we're going to take a different approach here. So here I'm actually, in some senses, this is the conclusion of my whole talk. This graph that I'm showing here, I'm showing a number of, oh, let's see, I wanted to turn on, so let me stop here and turn on the pointer. Now, can you see the pointer? Can you guys see it on screen?
Yes.
You can?
Yes.
Okay.
Yes.
All right, good. So I'm showing on this a number of energy sources. The renewable resources are on the left, and on the right, I'm showing conventional energy sources. And what I'm looking at here is the energy cost in the vertical per megawatt hour. And as you have undoubtedly noticed, at this point, the chart is empty. And the reason it's empty is because I want to explain a couple of key concepts first before I'm ready to show you the data, because I want to have a certain background before you see it, and I think maybe jump to the wrong conclusion. So let's see. Next slide. There we go. Next slide. Okay. So the first concept I wanted to cover is the levelized cost of electricity. So in this case, I'm looking at time 10 to 20 years and the cost per kilowatt hour. And let's suppose you have a 1 gigawatt wind farm, right? So wind is free. So the operating cost for a 1 gigawatt farm is fairly low, at least in this example, whether it's true or not. And then I'd contrast that with a 1 gigawatt natural gas plant. Well, natural gas is of course not free. It has to be extracted from the earth and piped. And so, this example, which is made up, but I'm showing here that the operating cost for the natural gas plant is 4 times higher than the wind farm. So does that mean that wind is 25% the cost of natural gas? Well, not necessarily, because the other thing you have to include is the construction costs. Suppose that the natural gas plant costs this much to make, and the wind turbines cost that much to make. Well, in that case, it's a lot less clear which of these energy sources is really the most economical, right? And to be fair, I should also at the far end here put what's the cost to decommission these plants as well, and capture all of these costs into the total cost of electricity. And that's what the levelized cost of electricity is. And so there's this, this is a well-established financial principle. And so there's a standard formula for doing that. And I don't want to go into this detail, but it's fairly clear that it's got all the kinds of things that you would expect as far as the discount rate of capital and the investment per year and the fuel expenditures and all things like that. So I think this is a fair way to capture the cost of electricity. And generally, when someone provides a cost of electricity, they're generally providing the levelized cost, but it's worth checking because, as I showed in that example, there's a world of difference between the operating cost and the levelized cost. Oops. Okay, so we're still not ready to show this data because there's one more point I want to cover in a fair amount of detail here. So here I'm showing, let's say it's an imaginary city, but let's say it's Los Angeles, California, and I'm showing the energy that's consumed over the course of one day. So here's midnight to midnight, right? And this is how much energy the people in Los Angeles want to consume. And as you expect, at 4 in the morning, people aren't consuming a lot of energy. At 6 a.m., they're having their espressos, and they're watching TV at night. And so you get some kind of shape like this. So that's the energy that they want to use up. And now I'm going to show what energy sources we have. Let's suppose there's a nuclear plant, which is very steady energy. And let's suppose there's a coal plant as well, which in this case, I assumed it was steady. And since this is Los Angeles, there's a photovoltaic farm somewhere out there. And the photovoltaic cells are only going to provide electricity when the sun's shining. And let's say near Mojave, California, there's a wind farm as well that's providing electricity. But in this case, I just made it up, and the wind's running in the morning and it dies at noon and comes up again in the evening. So if I combine all those energy supplies, we end up with the purple curve I've shown here. And when you look at this, it's pretty obvious. Well, the supply doesn't match the demand. Sometimes it's more and sometimes it's less. So what do we do in those cases? So let's first talk with the case here. This is when our supply doesn't meet our demand. So what are your options there? Well, maybe, hopefully, in the future, we'll be able to pull energy from storage to meet that demand. I have to be a little careful about that, though. And that's kind of my next talk about energy storage, but just a little bit here. So I think many of you may have seen this is the plant that Tesla built in Australia to back up a wind farm. It got a tremendous amount of press. And it's doing well for what it was intended, but it's 194 megawatt hour battery storage. And as I said before, a typical nuclear or coal plant is 1 gigawatt. If you wanted to back up a 1 gigawatt plant for 6 hours, you would have to take this Tesla plant here and you'd have to make it 61 times larger. So that's a lot of money in batteries and a lot of space. And then you've got to say, well, is 6 hours really enough? I mean, suppose the wind's not blowing for 5 days, right? Then that's a whole nother magnitude of battery storage you're going to need. So today, there's some cases where we've got pump storage and things like that, but we're not really pulling from storage much today. Okay, so other options you've got to make up is you can buy power. And buy power from your neighbors. And I understand California does this quite a bit. About a third of the power that California gets, they buy from out of state. And this is one of the kind of the overall lessons for renewable energy. It's balancing of energy. Hopefully that when Sacramento needs power, San Francisco does not, and you can level out the demand in that case. And that's a great idea as far as it goes. Now there are large grids in the United States. This is showing the large grids. Now, having said that, there are political issues that the people don't necessarily want to sell power to their neighbors because they want to have cheap power where they are. There's a limit to how far you can send power on transmission lines, and high power, high voltage transmission lines are also rather expensive to put in. So this is done quite a bit, but this is not, the ultimate solution. Your neighbor may not have power to sell you as well anyway. All right, and then, unfortunately, the most common solution for doing this is putting in a separate plant. A peak gas plant is typically what's done. A dedicated plant that's meant to meet these peak needs. It doesn't last for very long, but you have to incur the cost of putting in this plant, and then, of course, operating this is fairly expensive as well. Okay, on the reverse side, in the fortunate case when you've got more power than you know what to do with, what do you do with that? Well, again, maybe in the future you send it to storage, maybe you make hydrogen, maybe you desalinate water, you do something with that. Maybe you sell it to your neighbor, that's great, but unfortunately what's done quite a bit today, at least in California where they have a lot of photovoltaic, is they just turn them off. They just can't use the power. There's no place to send it, and so they don't make use of that power. Now, to some extent, this isn't really an issue just with renewables. Even with conventional energy sources, you'd need to have some kind of plant to meet the peak power. But it's an order of magnitude more significant problem with renewables because they're just so intermittent, right? There are certain applications, and this is really ideal. Like if you want to use photovoltaic to run your air conditioner, now that's a great match, right? Because chances are when the sun's really shining and you got that photovoltaic, then people are going to want to have the air conditioners. But if you're trying to heat your house in Texas in winter using solar panels, that's not a very good match, right? Or if you've got wind turbines and the wind's blowing at night, well, there's not a lot of demand for electricity at night. So that's not a good match either. And the intermittency, like I said, also could be the wind may not blow for not just 3 or 4 hours, it may be days, right? So in the next chart, I'm going to show the cost of the renewable energy sources, the levelized cost, and some of them are very good. But the caveat is, well, yeah, but what do you do when it's not available? If you include the cost of putting in a peak power plant or a massive battery farm, it's not as economical as the levelized cost of electricity would lead you to believe. All right, so with all that preamble, I'm finally ready to show this. So this is showing, as I said, the renewable sources. We're going to go through each of these in detail, so I'm not going to say a lot now. And then I've got biomass here, which is unfortunately one I'm not going to cover. Honestly, I think it's an abomination. I don't think we should be growing crops for fuel. I think it's terrible, but in interest of time, I just wanted to make this an hour and a half long. So maybe that's something we can cover later. So looking at conventional sources though, so this is gas, a combined cycle, which is a very efficient power plant. The cost is pretty good. Coal, you've got this massive range in cost depending on what environmental regulations are put in place. So old plants would be inexpensive, new plants would be very expensive because of the carbon capture they have to do. Nuclear, as we talked about last time, unfortunately, nuclear is fairly expensive. And again, there's a wide range, depends on the regulations. And the last one here is this gas peaker plant that I said was, this is just meant to fill in that short time duration, which you've got to build the plant. And as you can see, it's not all that efficient. So the cost of electricity is fairly high for those as well. Okay, so now we're going to go through each energy source, and I'm going to start with solar cells. So this is the world's largest solar plant. It's in India, and it's 2.25 gigawatts. And you're going to get tired of me saying this. This is the the capacity, that is the word they use, meaning in the best case, you're going to get 2.25 gigawatts. Obviously, you're going to get nothing at night, right? All right. So I wanted to say something about the physics of each of these energy sources. And so for the solar, this shows that the light we get from the sun, the solar energy from the sun, is about half visible and about half infrared. Up in space, you get about, above the surface of the Earth, you get about 1,360 watts per meter squared. On the surface of the Earth, you get, at best case, 1,000 watts per meter squared, which is quite a bit, really. It's impressive amount. And this is showing a cross section of a silicon photovoltaic cell. So at a very high level, photons hit the photocell, they hit the depletion region, and they hit an atom, and it makes an electron hole pair. The electrons are swept one way, and the holes are swept another way, and that forces a current to go through the circuit, which generates electricity. I'm skipping over a lot there. Now, it turns out that only a small fraction, or only some fraction of the photons that hit are able to make these electron hole pairs and make electricity. And, this is, I think it's a fascinating phenomenon. Originally, I had 4 or 5 slides on this. This is actually to understand this is what Albert Einstein got his Nobel Prize for in 1921 for the photoelectric effect. But I decided to keep this talk under an hour. I'm not going to go into the detail on that. I'm afraid I would bore you as well. So, but the summary I can provide in the next slide here. So I'm going to kind of walk through this. So I'm showing here band gap of a number of semiconductors. And so band gap is an intrinsic attribute of different semiconductors, and the band gap tells you what voltage you'll get out of the photocell. And then on the vertical axis, I've got efficiency. And you'd like the voltage to be as high as possible because there's more power at higher voltage. And so you might say, well, I'm going to use zinc selenide as a semiconductor. I'm going to make a photocell, and you get 3 volts out, which is great. But the problem is, of the instant sunlight, only a tiny fraction would be used into the conversion of electricity. So that's not going to work for you. And if you go to the other end of the spectrum and you make a photocell out of indium arsenic, well, in that case, just about all the photons are going to be turned into electricity, but the band gap is really small. So you only get a 1/4 volt out. So you're not going to get much power that way either. So as you can see, there's kind of you reach a maximum where you're getting a reasonable voltage and you're getting a reasonable fraction of electricity. And that maximum, silicon is pretty close to that at 1.12 electron volts. And the maximum efficiency you can get is about 32% from a silicon filter cell. Now that's kind of theoretical maximum. Typical best is like 20%. And there are different grades of silicon photovoltaic cells you can buy. Monocrystal at 15 to 20, polycrystal and thin film, with obviously the more expensive being monocrystal. Now, 20% efficiency doesn't sound that great, you might not think, but if I compare it to conventional energy sources, there's this gas peak plant that's only 25%, nuclear is only 33%, coal and steam, it's not until you get to a natural gas, the combined cycle I showed, or hydro, that you really get fairly reasonable efficiencies. And sunlight's free, so to some extent we're not as concerned about it. Of course, we want the efficiency to be as high as possible, though. So as you can imagine, there is tremendous amount of research going into making photocells more efficient. And so this is a chart that I stole from Wikipedia. It's a little blurry, but it's showing from years from 1975 up to 2015 or 2017. And it's showing the efficiency on the vertical axis for a whole bunch of different photocells that are under investigation. Being developed. And one thing you might notice is I said the maximum efficiency is 32%, and yet we've got solar cells with efficiency greater than 32%. And the reason that's possible is because my analysis was for making a photocell out of one semiconductor, Now, if instead you're willing to use layers, multiple different semiconductors, then you can kind of tune different semiconductors to pull out a different band of the sunlight, right? And in theory, if you had enough layers, you know, if an infinite number of layers, you could get up to 100% efficiency. Now, the record today is 47.1% efficiency. That's a 3.5 solar cell. It's made up of 6 different photoactive layers. And because you've got metals and oxides and things like that, in total there are 140 layers altogether in that. It's got great efficiency, but of course it's really expensive, right? So it's not really practical for powering the United States. For satellite or something like that, it's attractive. But I do think we're going to continue to see progress in the efficiency of solar cells. So this is showing the cost. So you can see why solar cells are very attractive. The cost is around I don't know, $30 to $40 per megawatt hour. This is for utility. Interesting. In contrast, I'm also showing here residential solar cells, which are quite a bit more expensive. And reading on the web, it looks like there are 3 reasons. One, you know, the most obvious is, of course, with your utility company, you're buying hundreds of acres worth of solar cells, and you get a much better price than a residential home does. Utility is going to do a better job orienting the cells toward the sun, and they're also going to clean them regularly. It turns out that, you know, dust and stuff on the solar cells can really impact their efficiency. So I'm not saying that you shouldn't put solar cells on your roof. It may make sense. You're just not going to get the same deal that you're going to get from the utility company gets, but this price is very attractive. So the growth rate for solar cells from 1992 to 2017, where I pulled this figure, is 29%. So say that again. 29% compound annual growth. I mean, that is just an astounding number, an incredible growth in solar cells. And it's the reason why, you know, when I went through the renewable energy sources, that I put solar cells first. Now, admittedly, they started at nothing, right? So so it's not hard at first, but they continue to be the leading technology for renewable energy. So these are the largest plants in the world. Not terribly surprising where they are. The biggest one is that one in India, 2.2 gigawatts. They are in places that are, of course, low latitudes, and the sun's shining all the time. They're hot and dry. You know, places like Florida, you get a sunshine, but they also get a lot of clouds, not as good. And so anyway, you see United Arab Emirates, China is not terribly surprising. And the United States doesn't make the list until number 14. Now, again, there's this capacity I'm showing. Just again, remember, capacity doesn't mean you get that power 24/7. All right, so I want to do some analysis. I think there's some misguided notions about renewable energy, you know, and I kind of wanted to address some of those notions. You know, the first is this question is, can we meet our electricity needs by putting solar panels on our roof? And I think I'm going to show the answer is no, but let me walk through that. So first, some data. This chart here is showing the irradiance for United States. So this is showing kind of averaged over a full year. And I think this chart is kind of what you'd expect. You know, places where it's low latitude and where you don't get a lot of clouds are the best places to put solar cells, right? Now, the scale here is a little bit hard to read, so I zoomed up on this. And what these color codes are showing is basically it's energy, kilowatt hours, how much energy per meter squared per day. And this is on average for the whole year. That's what it's showing. And for the analysis that I'm going to do, I chose to choose a value of 5, this orangish color. So it's applicable to kind of like this portion of the United States, right? So how much area would you need on your rooftop to meet electricity needs? Well, earlier I showed that chart of power needs, and one of them was for the average US home, they consume 1.25 kilowatts of electricity on average 24/7, right? And so I choose that number, and then I use the 5 kilowatt hours per meter squared per day that I think on the last one. And then I assume 10% efficiency for the solar cells. And I said the maximum was 20%, but there are fill factors. And actually, as I'll kind of show in the next example, this is actually fairly optimistic number. So from that point, from these numbers, it's really just fairly basic math then to figure out the area. And the area you need is 25 feet by 25 feet on a side, right? That square that big. Now, a couple caveats on this. First, that assumes perfect storage. So you're only going to get this power from the solar cells, of course, when the sun's shining. And at night, you're going to want to draw it back. And so you're going to have to put in some kind of battery. And the battery is not going to be perfectly efficient. So you're going to need more area than this if you include the losses in the battery. And the other thing is, I'm not including electric vehicles. You know, we're of course using more and more electric vehicles. So I think it's reasonable to say that our electricity consumption in the future is going to be higher than what we need today. So both of those factors are going to make, and plus my somewhat optimistic 10% is going to make this area bigger. So how do we feel about that? Well, you know, I'm fortunate enough to live in this wonderful green condo in South Waterfront. It's a great place to live, but there's obviously no way in the world you're going to put solar panels on the rooftop there that's going to provide all of us. But furthermore, I'd say if you look at most of residential places in the United States, you know, it looks something like this, right? And I think you're going to be pretty hard pressed to find that kind of area on your roof that's oriented well, that you're going to be able to get that energy from. Now, I'm not against people putting solar panels on your roof. That's fine, and it may make economic sense for you. But if you naively think we're going to solve our energy crisis just by putting solar panels on your roof, I think you're wrong about that. Okay, so the other question that's kind of related to this, that's asked all the time, is, okay, we're going to take them off the roof. We're going to put them on the desert. How many square miles do we need to just meet all of our electricity needs in the desert? And so that's another fairly straightforward calculation. So you look up and you find out how much electricity we use per day, and it's this massive number. And again, I use the 5 kilowatt and 10%. So I came up with a number that's 93 miles on a side. Now, it turns out this question is answered quite a bit online. And if you look online, the number that they come up with is 148 miles on a side. So in fact, my 10% was probably overly optimistic. This seems to be more the established answer. And again, I'm assuming perfect storage. I'm not covering electric vehicles. And then maybe biggest of all, you've got the transmission line costs. You've got to deliver that power to wherever you need it. So how do we feel about that area? So I'm showing here a map of the United States, and this is my original estimate of 93 miles on a side. And this is the more accurate one of 148 miles per side. You know, one of the things I like about science is you present the data and people can make up their own mind. This is often shown by people to say, oh, no problem. Now, you know, I happen to like Arizona. So the thought of covering Arizona with this large swath of photovoltaic cells, I don't think that's necessarily all that attractive. So I have some concerns there. And I guess I'd also mention now, so I'm going to steal something. I attended Ripu's talk a couple weeks ago, and I think it makes pretty valid the point that you know, the other question is, do we really have resources to build all these? And I'll talk about that as well when we talk about wind, about just kind of the amount of material it takes to make those. So I do have, and people can draw their own conclusions how they feel about that. Personally, I have concerns about blocking that much area in Arizona, and then of course, you know, you've got to transmit, and you need batteries, all that other kind of stuff. Now, to be fair, I will say that if instead of Arizona, if you move this to Texas, you know, and you don't get as much light, if you covered up the whole state of Texas, you know, I'm fine with that. So I'm open to that. Okay, environmental impact. So actually, I thought it was okay. So we'll go through this. There are obviously people that don't like solar energy. And there are a number of reasons. Now I think that with almost all of these, one of the key messages I'm trying to send is the environmental impact is often land use. And when looking at all these, the metric you should look at is watts per meter squared. How much area does it take to generate that power you need? And so solar cells clearly have visual impact, and if it's in Nevada and barren land, maybe it's okay. But a lot of cases, you're taking away needed area that could be used for other things. And so I think there's clearly environmental impact because of that. Creating these things, it takes fairly dangerous chemicals to make them and energy to make them. Now, fortunately, it's a semiconductor process, and we've been making semiconductors for years, and we know how to deal with the chemicals and making semiconductors. May not be inexpensive, but we can cleanly, without destroying our environment, make these. So I think that's okay. Disposal side, it's the same thing. These things last about 20 years, and again, disposing them, you dispose of them like electronics, which can be expensive, but I didn't see the environmental impact as showstoppers for this technology. Okay, and then I guess at the end of each section here, I kind of have this pluses and minuses to see if there's anything that I missed, but I think I covered all of that. So on to next section here on wind, and happy for me, once again, I got to talk about the Pacific Crest Trail. So I hiked through this area when I hiked the Pacific Crest Trail. This is Alta Wind Farm near Mojave, California. Really a miserable place. Dry, windy, unpleasant to hike through. This is a 1.5 gigawatt wind farm. It's the third largest onshore one, and it means it's the third largest wind farm in the world. So again, some physics here. What I'd like to do is show, I thought this was kind of interesting, is show that the power you get from the wind in a wind turbine goes as V cubed, and it's the same thing when you're driving or riding a bicycle. So I know that if I'm riding my bike into a headwind that's 10 miles per hour, and then I ride into a headwind that's 20 miles per hour, it's not twice as hard, it's 8 times as hard, because it goes as the cube of the velocity, and it's not too hard to derive that. So I will try to derive that now. So you've got a wind mass that's hitting the turbine here, and it's moving along, and there's kinetic energy associated with that, and it's kind of in the mess. I'm kind of viewing this almost as an energy density, but the kinetic energy goes as 1/2 mv squared. So I've got v squared already, and I'm trying to get to v cubed. So I'm trying to look at the power. So the power is the total energy over time, like how much energy passes through that turbine in a second. And the energy then is because I kind of view this as energy density, it's the kinetic energy times the volume. So now I'm going to switch to figure out what volume of air passes through that turbine in a second. And roughly a cylinder of air passes through this turbine every second, and the area of the cylinder is pi r squared, where r is the length of the rotor. But the length of the cylinder, how much in 1 second, how much air passes through this thing? Well, the length of this thing is also dependent on velocity. The higher the velocity, the longer the cylinder of air that passes through. So the length is velocity times time, and that's what's giving me another factor of velocity. And so you calculate the volume, and then I can go through the math here, but it's fairly straightforward. But the conclusion then is you get the power of a turbine goes as the square of the radius and the cube of the velocity. Now, there is this Betz limit. This is obviously a very simple analysis I've done. The Betz limit says you can get 59% of the energy from the wind, so you can't get all of it. This is showing kind of the operating mode for a typical wind turbine. So obviously when the wind's low enough, it doesn't turn on at all. And then at a certain speed, in this case, it's 8 miles an hour, there's a cut-in speed. And I understand on the big turbines, they actually have a kicker motor to kind of get the blades going at first. I'm sure that's a hard part. And then the blades start spinning, and they spin faster and faster and faster. And eventually the blades spin so fast that they're at the maximum that the generator inside of the turbine can handle. And you don't want to spin any faster than that because you could burn out the turbine. So at that point, then they feather the blades so that it doesn't spin any faster. And this region is called the nameplate capacity. Now, again, I'm going to say, you'll see a 2 megawatt or 5 megawatt wind turbine. That's best case, right? When the wind's in this region. Obviously, when the wind's not blowing, you're not going to get that. Now, above a certain speed, then for safety, they turn off the turbine, and for fairly obvious reasons, but just some fun pictures. If you run it too fast, you can get things like this or things like this. And then online, I saw a lot of pictures like this, and I suspect this is what happens when they aren't able to feather the blades. That part breaks, and so the turbine just spins and spins and spins. And you can imagine what a bad situation. You've got wind blowing at 40 miles an hour. This wind turbine is sitting above a dry farmer's field, and you've got burning pieces of material falling onto the field. And as you can imagine, there have been a lot of fires caused by turbines that have this failure mechanism. Okay, so now where do you place the wind turbine? Well, the answer is you place it as high as you can put it. So this is showing wind speed on the vertical axis, and this is altitude. Now this is altitude in kilometers. So to bring it down kind of a little bit more to our level, I'm going to zoom in, and this is showing. Now this is still extremely large scale because Everest is up here above 8,000 meters. But it's showing what it's showing is that the further you get away from the ground, there's this rapid increase in wind speed. So it really behooves you to be as high above the ground as possible. Yeah, you want to make the rotors as big as possible, but also there's a big desire to make just put it up higher. So it's not surprising that a lot of wind turbines are placed on ridge tops, like showing here. I mean, I think we're all aware. You go on the ridge top, yeah, that's where you're going to find the strongest wind, right? Now, it's also led to just some wild things. I said the higher up you get, the more wind. So people are looking at, things like this, the dirigible that, maybe you put it up 2 kilometers up in the atmosphere to harness the wind. Now, these aren't practical today, but who knows? And they've got things like this, which is basically a big kite. It seems kind of crazy, but, who knows? Maybe that'll work. All right, so I want to spend a little time on this. This is showing kind of the progression over time, how these turbines have gotten bigger. And, it's pretty obvious that they've gotten taller and that the rotors have gotten bigger. And so this chart was probably made in about 2015. That's the last data point. And so this one here is a 2 megawatt turbine. Now, again, that's the nameplate capacity. And I suspect in the Columbia Gorge, I'm guessing a lot of those wind turbines were made in 2015, so they're probably 2 megawatt wind turbines. So I think there's another misguided notion that some people have that we are going to replace our electricity and we're just going to put in a few wind turbines and we'll be fine. And so I kind of want to show you how many wind turbines it takes. So, a typical power station is 1 gigawatts, right? So if you use 2 megawatt turbines, you're going to need 500 of them. That is a lot of wind turbines. And now, in fact, the capacity for these, because the wind's not always blowing, of course, it's about 30%, right? To make up for the fact that the wind's not blowing all that. So rather than needing 500, if you want to replace a 1 gigawatt power station, you need 1,666 2 megawatt turbines. And then, of course, the power is intermittent. So you're going to need battery storage and stuff like that. So, the notion that we're going to replace our power stations with just a few turbines is really, not true. And then if I look at United States, if I look at the power, it's the equivalent of having 450 1 gigawatt power plants in the United States. So that would mean we need, doing this 30%, we need 750,000 turbines if they are 2 megawatts and storage. And so, again, this is a point that Ripu made in his talk a couple weeks ago, which I'm latched onto. And, you get into real questions of whether there's really, enough material, steel and stuff like that to make all these wind turbines, right? It gets to be some real issues there. Okay, so what's the trend in these? These have gotten bigger and bigger, and one of the things that I think is kind of funny about this is that it's already wrong. So they were predicting in 2030 you'd get a wind turbine of this size, and here we are in 2021, and the world's largest wind turbine is shown here. So, you know, where is this curve? I mean, it's fascinating. I think mechanical engineering standpoint, if there was like retired mechanical engineer that wanted to give a talk about wind turbines, Bruce Ellison, I think that would be really fascinating because I don't know where this is going to go. All right, so the biggest one here, I've got a picture of it. So this, the GE Halide X. It's 220 meter diameters. It's 260 meters off the high. And unlike the 2 megawatts, so that's a 14 megawatt wind turbine. So that does change the math some if they're going to get that big, right? You need a lot fewer of them. But now these things, this turbine is a monster, and it's hard to tell how big it is from this picture. But I found on the web kind of this is a zoom up of this region, and you see the people next to it, right? So look how big this thing is. It is giant, right? And then this is a picture of the blades, one of the blades. Right? Yeah, just I'm not a mechanical engineer, but part of me is just drawn. It's just fascinating to think of making something like this. Okay, the next question is, I said you want to put the turbines as high up as possible. Where about geographically? So I'm showing here mean wind speed in the United States. And you notice that there are some places where there's not much wind. Now, just by luck, those happen to be pretty good places for solar power. There's no physics reason for that, but that's kind of a nice coincidence. But when you look at this, pardon me, one of the things that jumps out is that where's the wind? The wind is on the coast. The wind is along the ocean. Those are the places of highest winds. And if I look at the world map, yeah, you just see this even more so. We're all aware that, Antarctica, people race boats down there and around the world. It's these hellacious winds. The North Sea is known for, rough, horrible, windy conditions. This chart, I used to want to go to Greenland. I don't know if I want to go that much now that I see how windy it is. So, but the message is, if you want the best winds, well, you don't put the wind turbines on the land, you move them offshore. And so this is a picture of an offshore site. Now, there are issues with this. It's a salt environment, and so there's more corrosions, there's more maintenance. You've got to put transmission lines on the seafloor. You've got to be able to service these things. So this isn't a slam dunk, but it's definitely a trend that's going, and it's driven by the fact that the winds are there. But there's another factor, and that's, as I said, the turbines are getting bigger and bigger. And if you're going to put them on land, they're in remote places, and it's getting more and more difficult just to figure out how to deliver those blades on land, right? You look at this this truck here with this contraption. That's quite a sophisticated vehicle to try and deliver blades. And in contrast, if you're gonna build them out offshore, then that logistics is a whole lot easier, right? Okay, so this is showing the cost, the levelized cost for electricity. Wind is very competitive. Again, it's like, I don't know, $25 to $60 per megawatt hour. This is showing onshore. Offshore at this point is more expensive, but I think this is the area that people are investing more. So I think this is going to come down and become more competitive as time goes on. Compound annual growth rate is 15%. Not the stellar number we saw with solar, but still quite respectable. And I think we'll see quite a more wind in our future. Places with the most wind farms, the United States does pretty well here. So this chart here is onshore, and China's got the biggest one at 8 gigawatts, but United States has got a number of them. And then this is offshore wind farms. All of these are on the smaller side. 650 megawatts is the biggest one. And the North Sea, right? United Kingdom, Netherlands, Germany. But I think as I said, these are growing more and more. Environmental impact. Okay, so certainly people protest these, and I've seen people protesting. I've seen signs up when I rode through Canada that people didn't like wind turbines. So once again, land use is probably the biggest factor. Now in wind turbines, you can dual use it. So if you've got crops or want to raise animals, I think it's wonderful in that respect. And overall, I'd say the environmental impact for wind, I think is probably the least of all these renewables that we've shown. There's a visual impact. So I understand the coast of France has got some really high winds, and it'd be a great place to put a wind turbine, but you're not going to put one by Mount Saint Michel, right? You don't want to wreck that. So there's some concerns about visual impact of windmills. Noise pollution is something that I think people are protesting about most of all. There's this chart which is provided by GE, and they're showing how much noise there is as you go away from a wind turbine, and they're showing at 400 meters distance that it's about as loud as a refrigerator. Now, this is a chart that GE provided. They don't say what kind of refrigerator you have or how big the wind turbine is. So I take this a little bit of grain of salt, but I would encourage, if you haven't, next time you drive by the gorge, you get out of your car and see what these things sound like. I can hear them, but I didn't find it to be that loud, and I didn't find the noise to be all that objectionable either. So I personally, I don't see noise pollution is that much of an issue. Bats and birds, I think that gets a fair amount of press. There are certainly concern with birds dying in wind turbines. Just this picture of the raptor here that died in a wind turbine. But if you look at the data, and that's what I'm showing here, so wind turbines, it's on the bottom of the Pareto chart. I mean, it's nothing compared to cats and vehicles and buildings. Now we are building more wind turbines, so this is going to go up. And I'd also say that cats are probably not going to kill raptors. So, there's more data you need, right? So maybe these are somewhat more selective, but it doesn't seem like death from bats to bats and birds are necessarily, that big a drawback, environmental impact from wind turbines. Now, you do have to recycle the blades. They last about 20 years. And there's this cute picture I found on the web of it's probably Denmark, where they turned it into a playground. That's cute, but obviously you're not going to be able to do that very much. So, but it's not rocket science. These are fiberglass blades or something like that, and we can find out ways to recycle them. And then, there's actually a positive side for these offshore ones. It turns out that the wind turbines make a good marine environment, and so there's actually a positive environmental impact in that case. Okay, so pluses and minuses. I think I covered most of these. I guess maybe, just wind turbines are often in remote locations, and so the politics of putting transmission lines in and the cost is something I probably didn't emphasize. That is a real concern with wind power. You've got to take the cost burden for that. Okay, so those are the two main ones. We'll go through a little bit faster now. So next, I'm going to talk about hydropower, and in this case, I'm showing Three Gorges Dam, which is not only the largest hydropower plant, it's the largest power plant of any type at an amazing 22.5 gigawatts. So what do you need for a hydropower plant? I think most of us know kind of roughly how it works. You've got a reservoir where you can store all this water, has all this potential energy. You run it through a penstock is what it's called, and drives a turbine that then generates electricity. So you need a number of things. You need a large flow of water. Now, the Mississippi has a large flow of water, more than twice the Columbia, but no one's suggesting that we dam the Mississippi. So in addition to that, you need a vertical drop. Ideally, you've got a vertical drop in one place, like Niagara Falls, which is great. It's got a lot of water, and there's a vertical drop, and not surprising, there's a big hydropower plant there. But the vertical drop doesn't have to be all in one place. There are these weird structures like this that sit out in the river, things, the propellers under the river. Now, these are not really that practical now, but on the practical side, you don't always have to have a vertical drop in one place. The run of the river dams is what they're called, and probably the best well known is in our own backyard, Bonneville, and that we don't have a large reservoir behind it. But nonetheless, you still have a vertical drop associated with it. The Columbia drops along pretty rapidly. The water is a fairly high velocity, and so that vertical drop that's in the flow of the water is what powers that dam. Obviously, you need rainfall, which is why the Pacific Northwest and Scandinavian countries are great for it, and Africa is not that well suited. You need a way to contain the water, so ideally you have steep walls on the sides so that you can build up, place a dam and build up this large reservoir to trap all the water. So there are a number of conditions you need for hydropower, and then the question is, how many places meet these requirements? And then how many of these places already have dams already? Hydropower is not new. There are references to hydropower from 500 BC. So my claim is that, yeah, hydropower is great, but we've kind of tapped it out, at least to a large extent. So this is showing the cost for hydropower. Yeah, very, very cost competitive. I like it. But you look at the estimated compound annual growth rate for hydropower through 2030, 2.4%. So I know there are a lot of people that like hydropower, and I like it too, but I don't think that hydropower is going to be our solution to our next energy source. Places that have the most of them are China, a lot in South America, Brazil, Venezuela, Canada, and then Russia, and really some massively large number here. It's 22 gigawatts, 14 gigawatts. There's no doubt the hydropower is a great source. Now, environmental impact, I think I've met some people that are all gung-ho about hydro and don't think there are really any environmental impacts. So I hope to disabuse that notion as well, because there are a number of things to be concerned about. Now, the first, once again, is land use. How many watts per meter squared does it take to generate the power? So places they're talking about putting dams are places like the Amazon basin, right? Now, we've all seen the stuff about the carbon capture capability of the rainforest and how great it is, and the biodiversity, and how is this treasured resources. Is this really an area of the planet that you want to flood and put under a large reservoir, right? Is that what you want to do? I guess I'd question that. So Churchill Falls in Canada. I don't have a picture for this one. Most of us liberals love Canada. I would say in this case, they made a reservoir there, and the reservoir was the size of the state of Delaware. Massive reservoir, horrible watts per meter squared, right? So I think that's a really big environmental impact. My own experience, I've been in Yosemite a number of times. Hetch Hetchy, one of the canyons in Yosemite, has been dammed for a long time. And do you really want to take one of the most scenic places in the world and put a dam in there, right? So land use is number one. Other things, there's concrete that's used in the construction of dams, and there's a lot of greenhouse gases. Now, if you look over the total operating cost, the the CO2 emission from the concrete drying at first is really not that significant. Fish, these days, I think with the fish ladder technology is pretty well established, so I don't really see this as that much of an environmental impact, but I put it on the list. Silt and beaches, you may not be aware of this, but dams have a really large impact on the beaches at the river that it flows into. So this is a picture of a dam that existed in 2011, and in 2011 it was removed. So up to 2011, the silt was not hitting this beach here, and this beach was getting eroded. After 2011, they removed the dam, and all the silt trapped up behind the dam was allowed to flow, and it rebuilt the beach here that had been eroded away for years and years beforehand. So a coastal erosion due to dams is a fairly significant thing. So something you probably hadn't thought of, malaria. So you want to build a dam in Southeast Asia or Africa, and maybe we'll eradicate malaria in our lifetime. But at this point, there are real concerns that the reservoir makes a great place for, unfortunately, mosquitoes to breed. And then finally, methane. So you make this reservoir, there's a lot of matter that decomposes in the water, and methane is about 30 times more effective than carbon dioxide as a greenhouse gas. So it's funny, you go through this list, and there are actually, quite a bit environmental concerns with hydropower. Pluses and minuses, I think I addressed that. Okay, next one, concentrated solar power. So this is in China. Really neat pictures. I love these photos of what it looks like. but hasn't really been that economically successful. And you can kind of see some extent. So this plant is a 100-megawatt plant. You know, it's funny that the last one was hydro at 22 gigawatts, now 100 megawatts. So a close up of this is where we've got a bunch of mirrors that are focusing the sunlight onto a column here where you're going to heat some liquid and make power. These pictures are a little bit sexier, but more typically is a parabolic reflector like this. And in this case, you've got this tube running down the middle, and the sun is going to be focused on that tube, and you'll put some kind of molten salt into it, and that will heat up, and then you'll use that to generate power. So solar thermal, you know, unfortunately, it's fairly expensive at this point. I would say that kind of the only caveat on that is, and I'll get to next, is there does have a built-in storage capability. So to some extent, it's an apples to oranges comparison to these other energy sources. But the compound annual growth for this is estimated 10% through 2025. Now, I'm skeptical on that based on the reading I've done to date, which says really I'm seeing everybody going to photovoltaic. So I question. Like I said, I'm certainly not an expert, but I don't know if it'll be that popular. Now, the one saving thing, the thing I really like about collected solar is the energy storage. So this is showing a typical plant. So you're taking something cold and it's going through these parabolic reflectors and it's getting hot. And then the magic is this hot tank here, right? This is really attractive because what it means is this thing can store the heat for an extended period. So you're going to gather all this heat in the day, and then at night when consumers, you know, want electricity, you can then flow the energy out and then drive a turbine. And so having that storage built in, you don't need, you know, a battery farm next to it or a gas peak power plant. So that is really attractive, but from what I've read and given the cost, it doesn't look like it's winning the race to be our leading renewable energy source. Okay, switching now to geothermal, which I think is the last one. So this is a complex north of San Francisco, an impressive 1.2 gigawatts. So this is showing the cost. So it is more expensive than a number of these other renewable ones, and the compound annual growth rate is only predicted 2 to 3%. And there's some real issues which I'll kind of go through in the next page. It's a little bit surprising. I've seen a lot of articles like this lately that are just really excited about geothermal. That, you know, geothermal is taking off. It's going to be the new energy source for the next decade, and a lot of optimism. But I'll go through the next page, my analysis. I'm not quite sure why people are so optimistic, because I think there's some real concerns. So this is showing a typical geothermal plant. Basically, typically you inject water into a well, and where there's hot rocks down here, and they're actually using fracking techniques to kind of break the rock. And actually, one geothermal plant had to be closed down in France because earthquakes were being generated. But anyway, you pass the water through these hot rocks, and then you pull it out. Maybe if you're lucky, there's enough pressure that just water will come out on its own. So the energy for geothermal, interesting, it comes from, I guess not terribly surprising, from the Earth's formation 4 billion years ago, and from the number of radioactive elements that are in the Earth's crust that are decaying, and those are generating heat. The total energy that the Earth is going to output geothermal energy is 46 terawatts. Now, our total energy consumption is 18 terawatts, and you say, well, that doesn't sound so bad, but that 46 terawatts is spread over the whole globe. You know, every volcano vent and fumarole and geyser and stuff like that, it's spread pretty thin. And if I compare that to solar, where we have incident energy of 173,000 terawatts, it's quite a bit different. The normal gradient, if you just took an arbitrary place and you drill down, it's 25 degrees C per kilometer. So if you wanted to get 200 degrees C, you'd have to go 7 to 8 kilometers deep, which is just not practical. So you can't do this anywhere. There are limited areas where it's viable to do a geothermal plant. The hot rock's cool, so you can't just pump as much water down as you want. You know, you're gonna have to drill in multiple places, and so there's a limit to what you can do, how much energy you can extract. And then there are just practical issues with pipes corroding, right? And you can imagine the maintenance, which is large reason why the cost is fairly high of dealing with this. Now, there are some pluses. Unlike all the energy sources, a lot of the other ones I've talked about, it's certainly not intermittent. You know, it's not just available during daytime, so that's really nice. And my thing, I've been trumping on watts per meter squared. Well, this is really great for watts per meter squared because all the action is happening under the ground, so you're not taking up a lot of land to make geothermal. So, you know, all these energy sources have pluses and minuses. Okay, so at this point, I'm ready to summarize. So I got this chart again. I won't say anything about it. We'll come back to it if there are people want to make comments. So there are a lot of predictions about the future and what's going to happen. And so I don't know the answer, but this is one prediction I pulled online that kind of matches what I've been talking about. It's showing that solar is going to increase rapidly over time, wind is going to continue to grow, and gas is going to continue to grow. Now, whether it can meet all of our energy needs or not is another question, but that's kind of the scenario we're seeing as far as the growth of these renewables. Takeaways, things I hope you got from this talk. So renewable energy sources are becoming more cost effective. You know, but you know, when someone says, "Oh, did you know that wind energy is now less expensive than fossil fuels?" I hope you'll say, "Well, yeah, it is, but if you have to back it up with another plant, then it's not the case. It's not so obvious, right?" Solar, photovoltaic, and wind are the leaders, but there's no single source that's going to be the answer by any means. Every energy source has its drawbacks. This how much watts per meter squared, and I talked about all the environmental impacts. And the next piece of the puzzle, kind of lead into my next talks, is energy storage is the next piece of the puzzle. So with that, last time I gave a joke. This time I don't have the same jokes. I just have this joke, which my girlfriend Bren gave me, which I thought was kind of cute. And then I'll end with this joke. So, but at this point, I guess we can open it up, and I welcome any of your input or thoughts.
Scott, can you hear me?
Yes.
You're gonna close? Yeah.
Yeah, I'll close it. I'm on it.
Okay. When we were in Costa Rica, they make a big deal about how they are all clean energy. And they have a lot of natural sources of geothermal. So in a way, it's based on where you are and what will work for you. I don't think you can decide in each individual place, we're going to put this in. Costa Rica just is one of the countries that took advantage of what they already had.
Well, I would argue Costa Rica is an exception.
Yes, I'm sure they are. And then when we also in Germany is bound and determined to make solar panels the way, and they're running into a lot of trouble because of that. Yeah, they're having a lot of problems, but they've really been pushing it. They've made it very cheap to install. And we were briefly in Germany, we were on a bus, but that's what we saw out in the fields, were all these houses with solar panels, much more than we see here, much more.
I'm not against renewable. I'm all for it. We definitely need to move renewable, but I think there are often naive notions that renewable is just going to roll in and it's going to be easy.
Right.
And that's not the case. As you said, Germany is really grappling with the intermittency of their power supply. They reached like 46% of their power coming that way, and it's a real issue for them now.
Yeah, Iceland is completely geothermal, and Costa Rica as well, but they are such small countries and such a small part of the GDP that really they're in the noise. So, I agree with Scott.
Scott, can I ask an easy, Di, turn yours down. I'll go over here. Unlimited energy with that, right? Easy questions, I hope. With the solar voltaics, you were talking about perhaps a maximum realistic energy of 20% efficiency. But all of the solar energy is being absorbed by those photovoltaic cells. And so you've got what, 80% of the energy being waste heat?
Yeah, that's my understanding as well. And in fact, you know, to get more efficiency, you're cooling some of these solar cells because they don't work as well when they're hot, right? So that is an issue. Yeah.
And
Well,
a lot of it's reflection.
A reflection. Okay. Thanks, John.
really? But they're black surfaces. Why aren't they absorbing virtually everything?
I see
What happens to the
Ripu
waste?
is shaking his head no. He's more of an expert than I am. So maybe he should answer it.
No, I mean, it is absorbed. It is it absorbs most of the radiation, and it does just it gets dissipated as heat.
But whatever you hit gets dissipated.
So anything above the one electron volt gets absorbed, but then it gets downgraded and you get only 1 electron volt
That's a
versus
good point. Yeah.
power,
Right.
and all the rest is
Yeah.
just dissipated.
Right.
Well, when you look at those huge farms, doesn't it have some kind of an effect on the land around it? And especially,
Sure does.
it does?
Of course, it creates these updrafts.
All right. That sounds like not a great thing.
Well, you
Well-
know, the trade-offs. There are trade-offs with everything.
Right. Right.
If the sunlight hits the object and it gets hot, if the object is the ground instead of a panel, it still gets hot. The heat goes somewhere.
Well,
Right.
no, you've got very reflective
It goes-
surfaces on most of the
It
ground.
goes somewhere.
Are not black bodies. That's the issue.
That's true.
I'll get off of that. One of the largest wind farm in the US, offshore wind farm that's just been approved, which is off of, I think it's going to be Long Island. Each turbine is going to be a mile from the next one. And this is to make the fishermen happy that they're not going to run into these things.
Oh, okay.
But
Interesting.
the area that's got to cover then at 1 mile each,
yeah.
it's enormous.
Yeah.
Anyway, great job. Thank you, thank you, thank you.
Thank you. Please open it up if people have strong opinions. You know, I shared my opinions. If you disagree with me or have other thoughts, you know, this is your chance, please.
Do you have
Somebody
thoughts
comment
about
on
the
the
future?
weather impacts of wind farms, because they're slowing down the wind and changing the weather.
You know, I didn't see, from my reading, I didn't see that.
What about the future? What do you see is on the next horizon here? That's,
You know, I'm going to punt to our expert again.
Mhm.
You know, Ripu, you want to take that?
No, I don't want to take it I don't want to predict. I know what I would
Okay.
see, but I don't want to predict what will happen.
I think, like I said, solar and wind are clearly the leaders.
They are the leaders. I'll agree they are the leaders. And as you were talking about the cost, and I'm glad you pointed out that levelized cost of electricity has been very badly used because it does not capture all the costs.
Right. So,
Even the people whose research, I'm having a senior moment here. I cannot remember the name of the person who initiated this, whose seminal work it was, made it clear it doesn't include these costs, but nobody else talks about that. Like the storage that is needed, the Rube Goldberg system that we build around to balance the intermittency is something totally lost. And those costs, when you add, it is not reflected in the LCOE, the levelized cost of electricity.
So one thought I had about the future, you know, I love that, you know, economic incentive that we've got to innovate and do stuff. So part of me thinks we're going to solve this problem because there's an economic incentive. The other part of me says we're consuming more and more energy every year, and the rest of the world is coming up. And part of me thinks, you know, it could be that our grandchildren or our great-grandchildren will say, I mean, you guys used to be able to drive a car whenever you wanted. That's crazy. How did you know? I mean, we may be in this rare time when energy is abundant, and that may not exist 50 or 100 years from now. We may all be living in condos like I do and taking public transportation because of energy. I don't know.
I think, remember the book Dune? They had that very scarce water supply.
Yeah, right.
Everybody had little things inserted in
Yeah,
their noses so they could recover the sweat and all that sort of thing.
Right.
You think about, you're walking around your house, right? You've got a house that's maybe 2,000 square feet or something. And I don't know what the volume is, and it's all heated.
That's
But
crazy.
the only thing that needs to be warm is you.
Right.
So a little space right next to your skin. And so the other thing I was thinking was, you got to throw in climate change. Look at the damage that can be done to these structures
Well, that's a good
by
point.
climate change. And also you're going to have to, you won't have ice. There won't be ice up in the mountains maybe. And now you're going to have to, those dams are going to have to be used to water that we're going to drink.
Yeah.
So there's so many things that are going to throw a curveball into what's going to be dealt with in the next 50 years to 100 years.
Yeah.
The surest way to assure that your children have a future is to not have any.
I've got an interesting data point here. I've had solar PVs, voltaic cells on my house in Beaverton for over 10 years now. So over that 10-year lifespan, and the system cost back in 2010, I think is when it got installed. The system cost us a little over $32,000, 10 kilowatts. And it's generated 158 megawatts of megawatt hours of energy, and that's consumed or generated 42% of my total house needs. Because I sell it back to the PG.
Yeah, right.
So
now, is that so? It sounds like it's worked out well economically for you. Now, were there significant subsidies in that in your math?
Yeah, obviously there were. Yeah, it doesn't, and even with those subsidies, it will not pay for itself. I don't think.
But they said
It
12.
will not. Is that right?
I don't think it will. I got a big tree in the backyard that's providing partial shade at times. When I first went in, that tree wasn't tall enough to shade some of the cells, but that's a problem. You have to really avoid the shade, and the cells have never been cleaned and never been washed.
Okay.
I've tried to find somebody to do that, and nobody. There is no business around that goes around, climbs on roofs and cleans solar cells.
Yeah. Okay. That is an interesting data point, and I think subsidies are often controversial, but people have also argued that, we've subsidized the oil industry for years and years through wars or whatever, right? And so subsidizing solar cells doesn't seem so bad, right? And I don't know the answer, but I think there are two sides to that.
I've got one here. Can I just hit one more time? The area that you're talking about, I think it's just a matter of the will, as far as, finding some desert areas that you're willing to just sacrifice in order to keep the electricity going. I think that if you really wanted to do it.
Well, you still have transmission lines, right? And you've got energy storage, but I understand your point.
It wouldn't be in one place, of course. You'd have to have it sprinkled around.
Right.
And Scott, when you were giving the analysis of how many, 1.25 kilowatts in the household, and said it doesn't include the electric car, but it also doesn't include the heating. Most of the homes are heated by gas.
Okay, thank you. So it's going to go up for that too. All right.
But
That's usually one of the trends is in this greener world, we're moving more and more to electricity, right? Even though it's more expensive, that can be generated cleaner.
Right, it's cleaner.
Yeah.
I did like Scott's suggestion that we just sacrifice Texas.
That'll save
Aren't France and Canada using a lot of nuclear power? Maybe we should not be too afraid to use that instead of fossil.
Absolutely.
So yeah, Ripu has made that argument. That's kind of his centerpiece now. And someone in the comments that Bill Gates had done that, has been pushing that as well. Now I would say in the last talk we talked about conventional energy, and boy, the political of, you know, I think you were probably in that, talking about energy, the waste disposal, and, you know, so I'm with you. I hope we could make it done. We can do it.
I think there's two things, if I could add. I think there's two things. One is that the costs that you talked about doesn't include the carbon costs. So what the future cost will be to adding carbon to the atmosphere is not included in that cost. And then the other thing
Meaning
is,
the fossil fuels are a lot more
Bruce,
expensive, right? That's what you're saying. The
Yeah.
fossils, yeah, okay.
and then as Bruce pointed out, you know, maybe we'll have less electricity available to us. I'm not so sure. I think it's just going to cost more. I think, you know, so if you go over to Europe and you pay $8 a liter or a gallon for gasoline, people tend to find ways to still drive and pay $8 a gallon for gasoline. Energy and fuel are probably going to go up. It's just a cost of what we're going to have to bear for our kids to have a livable planet. And it's just something we got to think about. But one of the things that the politicians talk about all the time is that it's going to cost more. It's going to cost more. And if people said, okay, then all of their arguments would go away as to using alternative sources of energy. So it's something that we're just going to have to think about. We've had a long run of very cheap energy, and, you know, and right now everybody's buying SUVs because you can buy gas for $2 a gallon. So why not get a huge car to take your kids to school, and
Right.
you know, you got 4 extra seats in the back.
More bicycles.
Hey, again, my Tesla is using like 10% the energy as my previous gas-powered vehicle.
Except
10% the carbon footprint.
Using Bitcoin.
But which brings
Oh,
up
yeah.
a question. You kept mentioning that it doesn't cover the car. What are the projections when everybody's got an electric car? What's going to do to this system?
Well, I don't know the answer. That's and the Ripu was saying we're moving more and more to heating and stuff. I don't know, Ripu, do you know projections of
The projection is by so total electricity production in the world is about 20,000 terawatt hours. Currently, we are going to be consuming around 110,000 terawatt hours.
So
Terawatt hours.
that's 5 times increase in what time frame?
The next 30 years.
Okay.
So don't get rid of your gasoline car.
Right.
Yeah, but the electric car doesn't reduce.
Rid of all the fossil. If you want to get rid of the fossil and replace it with electric sources, your electricity demand would be on that order.
So Wells, you have a comment on that, Wells? Sorry.
Well, but the electric car doesn't reduce carbon emissions. It gives you the opportunity to do it. But if you're not capturing at the power plant, it doesn't make any difference.
Well,
really.
so go ahead, John. You talked about this last time.
Yeah, no, I mean, last time Scott gave his talk, I went through the numbers. I mean, basically, you know, the amount of carbon that my Tesla produces is literally like 10% the amount of my previous gas-powered vehicle per mile.
All the way from the gas-powered plant all the way to your car.
That's correct.
Well, that was in Oregon, John, right, where we get half of our power from renewable, and nationwide it was still like 25%, right?
Yep, correct.
So it's 10 times better in Oregon, and the nation is 4 times better.
Okay, that's a good number. That's a good number I didn't have. Good.
Yeah. I read a report the other day that only 5% of Americans have electric cars right now. Certainly in the north and any snowy state, you don't get one because the capacity.
Yeah.
Significantly. But I want to make a non-technical comment. We have a corona pandemic, and that has changed our lives in every country so much last year. I love these little predictions of what we need to worry about, what will happen. But suddenly people are working out of the house, they're not traveling to work. Our whole society is changing dramatically. Whether it lasts or not, I don't know. But things happen, and we go bump in the night.
I'm kind of looking forward to my next
The whole world has.
analysis. My next electric car is really fast. It's a performance car.
Well, they still have-
So going back to Diana, basically you're saying things can change faster than we think? Is that your
yeah,
point?
and
or-
change the world. Who would have thought one little virus would affect every country in the world?
Yeah.
That's a good,
Well, in the last week, a number of auto manufacturers have declared that over the next 10, 20, 30 years, they'll only be making electric cars. And if that gets picked up by the rest of the manufacturers, then it'll no longer be an option for the rest of us.
Yeah.
So that is exactly where I came from. We own Volvos, and our Volvo came to us and said, going to be 20 in the next 2 years will be only electric vehicles. But then if you listen to them carefully, they said it is because it's going to be more profitable. They weren't really concerned about the environment.
John,
They
you
were
have-
going to make those vehicles more profitably
battery
and sell them with a greater business value.
Scott, do you have charts that show the environmental impact of all the sources of energy? I mean,
No,
the chart you showed was dollars.
Yeah, right. So there is, I talked about levelized cost of electricity. The equivalent is levelized carbon of energy sources. Because to your point, you may make a lot of greenhouse gases making the solar cells and stuff like that, right? And so while the photovoltaic cells in the field don't make any carbon, in the production they do. So there are such calculations. I sorry, I'm an amateur. This was enough to take this on. So maybe that's a project for someone else to report back. But I'd love to see that too.
Are you going to discuss in the next talk? You said it's energy storage. Years ago, there were proposals to take the daytime energy surplus and pump water up a mountain.
Oh yeah, pump water
Store
storage.
it potentially.
That'll be the first one I cover.
I haven't heard anything about that lately.
There are real proponents. I don't see it as that viable, but that's a good tease for the next talk.
in terms of carbon use, one of the things that Diana brings up, there are a number of things that I participate in that are now done on Zoom, which I would normally be driving to. This could have an enormous impact on what we could say.
Yes.
Well, I hope so. Now, how much of our energy consumption is transportation? Maybe a third? I don't know.
Yeah.
Cars and
Yeah,
trucks.
yeah. That includes cars, trucks, ships. Yeah.
Well, if it gets expensive enough, you know that the corporate people will find ways to not travel and not use as much energy.
We'll just Zoom.
Yeah, everybody's doing now.
Yeah. Well, there'll probably be other ways to save too that we haven't thought of yet.
But we have to think about the fact that there are about 1 billion people in the world who have no electricity, and about 3 billion people who have subpar electricity. And many of us in Oregon recently just went through a spell of no power for a week.
Yeah, right.
And we know what happens.
Yeah.
I mean, it is a severe loss of human potential. And I think the world cannot afford to let that human potential just go to waste.
I live in Palo Alto, and Palo Alto is trying to go all electric and get rid of any gas for all new construction, and not allow any gas fireplace. I mean, any wood fireplaces. The fallacy that's happening is the city has tiers in cost of payment, electricity payments. The more you use, the more you are charged. And so electricity is will be very, very expensive if we have electric cars and electric water heaters in our house. Of course, the city never mentions that because that's a big money maker. And it's something to consider in terms of what will be the cost to us if we go all electric.
Yeah, I think it's forward looking at Palo Alto to do that, but as you said, well, unfortunately, people in Palo Alto are rich, right? So it's a good place to try it, right? Boy,
48% rentals are okay.
yeah.
Another issue that is some of the sources we use for power is not unlimited. We can use up the coal, we
Yeah.
can use up the oil, maybe not in a lifetime, but eventually. Whereas when we don't use up the sun, I think some people that object to thermal energy don't understand that we're not taking something away from the sun. We're just using what they send us anyway. And so we have to look at our concerns for what are we using up? And that's a big issue for a lot of people, myself included.
Yeah, I agree that the nice thing about the sun is that it will be here hopefully hundreds of years from now, right? It's going to continue to be there.
Millions of years from now.
Billions.
Yeah, but about 4 billion years from now, it's going to become a red giant. The sun is not renewable. It will.
I knew John was going to say that. I just knew it.
Hey, hold it. You're going to have your day on the 24th, John. Okay, so here we go, guys. Here, John, I'm going to make a pitch here for John. John has this idea of, it's a lot of work for somebody to do a whole lecture. And most of the people that we've already gotten to do lectures have already done their lectures. Have a few of them that have a few left. But he said, well, how about you make a little mini 10-minute thing? Maybe it's a response to something Scott said, or it's a little, outtake on what the Decenovians are doing, maybe in your paper. Just something that if you had a little 10-minute thing on the 24th, John has one of his rants he wants to do that's going to take 10 minutes. And we're looking for maybe 2 or 3 other rants. If anybody had one, Tim, come on now. You can rant with the best of them, right? So if you could make maybe 3 or 4 slides and then have something interesting to say.
You mean you want me to talk about gears?
Gears, sure. I might do one on replicated mirrors. I've got a little presentation I did once. I bet nobody knows how they're made. It's interesting, but it's it might not get you too excited. John's will get you all going. So any volunteers, please send me an email. You know where I live. Ripu, maybe?
Sure, I will. I can rant for 10 minutes.
Okay.
You should give a full talk though.
I mean, you don't even need to have a slide.
Let me just make a plug over here. Later this month, I will be giving an hour-long talk to the American Chemical Society. A Zoom talk, and I'm going to send the link. And welcome to join. And the one that Scott that you heard me should be posted on YouTube very soon, or a link which should become available very soon. And I'll send
why don't you respond back to us all with that link then? That would be.
I will do that.
Yeah.
Hey, why don't you do that same talk here for
Bruce? I mean, I don't know if I can reply all, or should I just send to
Or
Bruce?
give the talk to us as well, so we can interact and ask you questions afterwards.
Okay, sure.
Yeah.
Okay, good.
Can you do one in April?
Sure.
Okay. Awesome. I'll find a date for you.
And I think Booker, who's expert on chemistry, we need to get him out here. Who else can I put on the spot, right?
Yeah.
Bruce is going to talk about windmills, right?
Someday. I actually have a nephew who, or sort of I don't know what they call your cousin's son, but he worked in that industry for a while, in the windmill industry.
Removed.
Yeah. Your cousin's son is your cousin.
Cousins once removed.
Yeah, true. Yeah. Okay, I think we should probably wrap it up. Yeah, it's 8 o'clock, and I don't know what the heck time. It's 11 o'clock for some of you people. So
yeah,
you get your bit by. So We'll see you next week. It's going to be, who's next week? Who is next week? John, is that you? John Wiltsey?
That's what you said, yeah.
Can't minimize this thing, so.
I got your slide up here. Let's see. Chaos theory, Ed Friedman.
Oh, yeah, Ed's not on today. Yeah. So we're gonna have Ed Friedman back. You've all heard from him. So it's good. He does a great job.
Yeah.
And we went from fractals and now we're gonna get to chaos. I think they're both supposed to be sort of the same thing. All right, so good night, everybody, and see you next week.
Good
Okay,
night.
thank you, Scott. Very, very
Very
enjoyable.
interesting
Thanks a lot,
stuff.
Lee.
Yeah.
Amazingly good.
Thank you.
Thank you, Scott.